How's it going there, Chem student? Welcome to the screencast for question 3 of worksheet 3. Here's how this IFE example reads. It says a flask of 205 milliliters. Hey, how's it going there, Chem student? Hopefully by this video you've tried successfully questions 1 and 2 in your IFE worksheet 3 packet. This is specifically the screencast for question number 3, which is a little bit different. They give us a new word. It's called puffs of particles. And I'll show you how to handle the problem when you receive this word. Let's go ahead and let's get started, and we'll go ahead and read the problem. Here's what it says. A flask of 205 milliliters of air contains 5 puffs of particles. The pressure probe on the flask reads 720 millimeters of mercury. What is the new pressure of the gas if an additional 5 puffs of air is added to the flask? Remember, our first goal is to find our constants and to eliminate those completely from our data table. So the first thing that I read that pops out at me is that we're using a flask. So they gave us the volume of this flask, but a flask is made out of glass. It's a rigid container. It's not going to change shape. It's going to hold its own. So long story short, what that's telling you is that the volume will remain constant. As I read through the problem, there was no mention of temperature, and whenever there's no mention of something, you as the reader can assume that that is also held constant. So just by doing those two things, we've eliminated this table in half. All we need to deal with now is N, the number of particles, and P, the pressure. Whenever you read puffs of particles, that refers to numbers of particles. So if we have 5 puffs, what we can write down is 5 under the initial spot for number of particles. What they also say is this, that we add 5 additional puffs, okay? So 5 plus 5 gives you 10 puffs of air. And this is a net increase in the number of particles. It says that the flask initially reads 720 millimeters of mercury, meaning that we want to find the new pressure. The new pressure, question mark, would be placed here underneath 720 because that is what we are trying to compute. Notice that we are dealing with numbers of particles and pressure, and as previously stated, volume and temperature are held constant. We will think of this setup as we look at our gas lab summary, and let's go ahead and pull that up so we can look at some relationships. So the column that we are currently interested in is this one, pressure versus number of particles. So if I go to the bottom, here's what it tells me, that there's a direct relationship between pressure and number of particles. When one goes up, the other must go up. When one goes down, the other must go down. So if we reference our table, we notice that the number of particles increased. That means that the pressure also needs to increase. A formula is needed to compute our value for our final pressure, and here is how the formula reads. Final equals initial times a ratio. Let's use the highlighter again to accentuate where information is being pulled from. Final is what we're computing. That is the question mark right here. Your initial value is always right above your question mark, and your ratio always comes from the column with both the final and the initial value filled in. My initial value, remember, was 720. And what I have to do is multiply this by a ratio. So the two choices that I have to multiply by would be 5 divided by 10 or 10 divided by 5. Well, I need to pick a number that will make 720 a bigger number because this arrow is telling me to do that, that 720 needs to grow. So if I picked 5 divided by 10, that would make it a smaller number. If you pick the ratio that has a numerator that's bigger than the denominator, that will make your number grow like the effect arrow wants us to do. So we'll go ahead and we'll copy this into the ratio spot, 10 divided by 5, and we'll go ahead and do this math together. Ten divided by 5 equals 2, and if I do 2 times 720, that gives me a grand total of 1,440 millimeters of mercury. And this is my final answer. This answer makes sense because it's bigger than 720. It follows the rules of this arrow that I just chose, and the answer finishes the computation for us. All that is left for us to do now is to make a particle drawing to complete this table. Remember, volume refers to your box size. N refers to number of particles, which is the N equals. T refers to the whooshies, which is my W equals. And then P refers to the pressure vents. And my recommendation is always to draw your box first and start from there. If you notice, our box size will remain the same because volume is constant. So as best as you can, draw the same sizes of boxes. Okay, perfect. The number of particles needs to increase because it goes from 5 to 10. So I'll write down n equals 2. We could double that to something like n equals 4. And you can go ahead and draw in your particles here. The temperature remains constant, so every particle will get a single whooshy. The temperature does not change from start to finish, but the pressure must go up. So in this first box, we'll have one pressure vent, and in the second box, we'll show 2 pressure vents. It doesn't really matter what numbers you pick, as long as you show an increase or a decrease. Here is one whooshy and one pressure vent. Here is one pressure vent, a second pressure vent, a whooshy, and a whooshy. So as you look from left to right, again, the volume remained constant as well as the temperature, but you will see more particles and more pressure vents to your right. Hence, this drawing matches our box. At this point, you would be done with question number 3 on your worksheet. And thank you for tuning in and listening. Please remember you can pause, rewind, and look at specific pieces again for clarification as needed. Thank you.